Okay, so now with the three main things we have, order of complexity, which will lead to rewrite rules, and superposition of critical term, which will lead to critical pair, and finally the confluence set, which will lead to canonical set that we need for the rewrite rules. Okay, we can now go on to explain how does the algorithm works, how does the Knuth-Bendix completion algorithm works. Okay, this is a simple form of Knuth-Bendix algorithm. Of course, there are different form of it, but this is one of the basic simple form of it. Okay, so we start off with we start off with a non-empty axiom set. Okay, so like for example, we have for the rewrite rules, we have the A1 to A4. So for this point of view, is still equation. So it's a x plus 0 equals to x. It's not yet the rewrite rule. Okay, then select an axiom for an axiom set, normalize it. Okay, so if there's if this is like at the some current certain stage of the algorithm, then you may have some rewrite rules, then you can normalize it. But at the start, there will not be any rewrite rules, so there's nothing to normalize it. So if the normalized axiom is not of the form x equals to x, then okay, order the axiom we using the complexity ordering, reduction ordering, and introduce a new rule in the rule set. Okay, superpose the new rule on existing rules, including itself. Okay, and introduce a critical pair into the axiom set. So after you superpose, you get a critical pair. When you get the critical pair, you can make an equation, and from here, the equation, okay, that you have, you'll go back to the axiom set. After that, same thing again, normalize it if there is. Then after that, from there, then you continue on, keep on doing this loop. Okay, while the axiom set is not empty. So what are the outcome? One is to converge. Okay, when it converge, the algorithm converge, it means that you have found a finite canonical set of rewrite rules. Fail. If a particular axiom cannot be ordered by the the reduction ordering, which I will show you the example later. And finally, to diverge, the canonical set is infinite, and this may be used as a semi-decision procedures. Okay, later I'm going to explain more about this. Okay, so let's see an example where the Knuth-Bendix completion converge. So now we have axiom A1 to A3. Okay, note that we take away the x plus 0 equals to x, the other direction of this. Okay, because eventually, if you notice at R8, it will eventually generate out. Okay, so start with this. Okay, then we try to superpose R1 with R1, R1 with R2, R1 with R3, R2 with R3, R2 with R2 itself, and lastly R3 and R3 itself. So whatever pair it is. So for the first one, for example, we get from R2 and R3. Okay, I'm gonna just explain one of them. Okay, so R2 and R3, we can superpose it. Okay, superpose the left hand side of R2 with the left hand side of R3, which is just now what we did for our example for negative A equals to A. Okay, in the one of the earlier slide. So this will be a resulting superpose result. Then after that, yeah. Okay, after that you can get into critical pair, you normalize it, then you realize, these two are equivalent because of the arrow, then this equals, this is equal, this is equal, this is equal. So we can form a rewrite rule using the ordering. Okay, hence, okay, they derive this new rule. Then after that, they continue on R1 with R4, R2 with R4, so we continue on and create more and more rewrite rule. Okay, it will terminate. Okay, terminate when all the pairings has been exhausted and no more new rewrite rules can be found, which means no more superposition and unification of the left hand side of all the new the 15 rewrite rules. Okay, no more pairing of the 15 rewrite rules that allows unification that will yield the superposition of critical pairs. So it will terminate and give you this finite set, canonical set of rewrite rules, R1 to R15. With this set, okay, if it's finite, it will prove valid So this shows an example of proof of valid equation. So I have this equals to this. Okay, which I think is one of the first slide, the very first slide or second slide of the whole presentation. Okay, so with all these rules, if you use the normalizing, if you normalize both of left hand side and right hand side, eventually you get the same and it's a unique normal form. Okay, and this will be, then this shows that this is a rewrite proof to show that this statement, this equation is valid. Okay, for invalid proof, this equals to this. Okay, you use all the rewrite proof like R10 and R2 like over here. Eventually you get the normal form to be different, and this shows an example of a proof of invalidity, invalid equation using the confluence set of rules. Okay, so I give an example of when the case Knuth-Bendix completion will fails. So for example, this is the multiplicative group axiom. Okay, so we make it into rules. Okay, so when it fails is when it hit this stage, which is the commutativity between two elements. So should we order x, y times x greater than x times y, or the other way around? Okay, so this is where it fails because you don't know how it can order and form a rewrite rule. So there have been ways to counter it and solve this problem. Okay, one way is to make some changes to a rewriting rule. So whenever this kind of situation happen, apply equation in either direction. So you don't need to from left to right or right to left. Okay, as in, yeah, you don't need. So for this equality, right, you can change from left only when this happens. Then you can change from left to right, because usually you try to rewrite from a complicated term to a simplified term, but from this point of view, we cannot really know which is more complicated. So we can allow rewrite from left to right or right to left. Okay, but with certain condition, only when its instantiated form after matching is orientable under the ordering, which means after using left to right or right to left, either cases, the next step after using, after that the next step, okay, must be able to get orientated by the ordering that we have defined. Okay, so this will prevent it to do like in the loop. For example, you write from left to right, right to left, right to left to right, right to left. Then for example, forever in this loop. Okay, which is not able to do it because of this rule. Okay, because after you have been initiated, okay, instantiated, okay, then it must be orientable, okay, under the reduction ordering. So if the next step, so after we write from left to right, you cannot rewrite from right to left, because after that you cannot make the ordering again, so it will get stuck. Okay, so another way is to superposition, allow superposition on both sides of the equation. So from what we know, we only allow superposition of the left hand side of the rewrite rules. Okay, for now, because of this, we allow superposition of the right hand side of the equation for this kind of scenario, if this kind of scenario happens. Yes. Okay, so divergent. So if the confluence set turns out to be infinite, no decision procedure is possible, because it will keep on generating and generating more and more rewrite rules in non-stop fashion. So in this case, it will be used as a semi-decision procedure. So valid equation may prove by running the completion algorithm long enough. So maybe this long enough can be very long itself, okay, to generate the rules required for a rewrite proof. So essentially, it's just you give in the equation that you want to prove that is valid, okay, then you keep on generating rewrite rules, which means theorems, more and more theorems, until you have enough theorems or rewrite rules in order to prove that valid equation. However, invalid equation cannot be shown invalid because it will run forever, because since that set of canonical or confluence set is infinite, you will keep on generating rewrite rules try to prove that equation, but actually it cannot be proven because it's invalid. So you keep on generating more and more rewrite rule, thinking that the equation can be proven, but in actual fact it cannot be proven. So you will never stop because you will keep on trying to prove it by generating more and more equation. Okay, rewrite rules. So some limitation of this Knuth-Bendix completion is that, okay, in practice, it's very hard to find a reduction ordering of this that suit the particular needs. Okay, so yeah, there are some cases where the ordering may not be that obvious for you to see. Sometimes, yeah, the length of the terms may not be so easy to order them. Okay, in many practical importance, so the confluence set of rules is infinite, and hence the algorithm diverge. Okay, so this is one of the major problems, because if infinite, the algorithm will keep on diverging, and we do not have a complete or full decision procedure. And if conditional axiom, there is a axiom that is conditional, it may generate meaningless terms. Okay, meaningless terms. So for example, x inverse of x, well, this is a axiom for the multiplicative group. Okay, then for this will, for x inverse x, will give you the identity matrix. Not the unit identity. Okay, then for x multiplied by 0 will give you 0. It give you 1 for this way. Okay, x multiply 0 to give you 0. But this case for R12, we need to make sure that x cannot be 0 itself. So this is a conditional axiom. However, if we ignore the condition and we use x as 0, you'll realize that after writing rewrite proof, you prove that 0 equals to 1, which is wrong itself. Okay, so you will give us meaningless terms, okay, which will yield invalid or wrong conclusion. Okay, because of the axiom is being conditioned that x must be greater than 0, for example. And lastly, the procedure is not goal-directed. The generation of critical pairs is based on the rules formed up to that certain stage, and is not motivated by the equation to be proved. Okay, so this is not very good, because usually when we write an algorithm, we need to have the goal in mind, so that the algorithm works for that goal. We do not, but for this case, it just based on whatever input axiom we have. All the new rule generator is based on what kind of input axiom we give him. Okay, and it's not motivated by, nothing to do with the equation that we're trying to, or the goal that we're trying to prove. However, there are works that work on this problem, okay, which is a goal-directed or goal-orientated Knuth-Bendix version. Okay, so yeah, you can search and look out for it. So in conclusion, what we have went through, Knuth-Bendix completion algorithm, a semi-decision algorithm that transforms a set of equation into a confluent term rewriting system. Why is it so useful? It's used for reasoning in an equational theory. How is it done? So there's 3 steps. Ordering of complexity will lead to turning equation to rewrite rules. Superposition of rewrite rules to generate critical terms. Okay, then which will lead to generating of more rewrite rules. Okay, then confluent set of rewrite rules. If it's finite, it will be a decision procedure. Okay, and if it's infinite, it will give you a semi-decision procedure where only valid equation can be proven, given enough time, if you run the algorithm long enough. Okay, so yes, so this is a set of reference that I use. Okay, so thank you for listening. Okay.